Turning all that energy from the sun into electricity means we need to have a way to collect it, convert it, and use it. Welcome to the world of photovoltaics. Break this mouthful of a word down and you have photo, meaning light, and voltaic, meaning electricity. This is precisely the mechanism we need to collect and convert sunlight to electricity. The idea is simple. Collect the sun's energy and use it to turn on the lights. The application is a bit more complex. We'll have to think back to what we learned about the sun, how it makes energy, and all that stuff about protons and electrons. Are you ready? All right, let's get going. Basically, solar cells are arranged in groups called modules to make a panel that, when connected to other panels, makes up an array that produces a certain amount of electricity. The cells themselves are made of semiconductors. This material, generally silicon wafers, absorbs the energy of light. Silicon is an element and one of the most abundant substances on Earth. Let's take a minute and explore silicon more thoroughly, since it plays such a significant role in solar energy, and as you'll find out, so many other things we use every day. The silicon story begins back in 1824 with its discovery by a Swedish chemist. It's officially the 7th most abundant element in the universe, following hydrogen, helium, oxygen, neon, nitrogen, and carbon. Just in case you're wondering, magnesium, iron, and sulfur round out the top 10. It's the 2nd most abundant element in the Earth's crust, right behind oxygen. Silicon forms many useful compounds. Silicon dioxide is a nifty way to say sand. But this compound also occurs in minerals of different crystalline forms, like quartz, amethyst, and opal. SiO2, or silica, is used to make bricks, glass, and ceramics. And you know those little packets you find in new clothes, stuffed in the pockets or hidden in a pair of shoes? That's silica gel, a form of silicon dioxide that's great at absorbing moisture. Silicon carbide is used as an abrasive because it's extremely hard, like a diamond. Silicone, as you might have guessed, is made from silicon and is widely used as a lubricant and polishing agent. But we're talking about solar cells, so where does silicon fit in? Crystalline silicon has 14 electrons arranged in 3 different shells. The first and second shells are full, leaving 4 electrons to the third shell. This is only half full. There are 4 empty holes looking for 4 other electrons. This makes it easy for another silicon atom to link up, sharing its 4 outer shell electrons, and in essence, borrowing 4 from another atom. This can happen in many combinations too, allowing an interlocking system of shared electrons to form a network, or crystal. While it makes for a beautiful labyrinth, it isn't very useful for conducting electricity. You see, none of the electrons is free to move around. They're all locked in this structure. But scientists have discovered that by mixing silicon with other elements, the conductivity increases. Solar cells are generally made of silicon mixed with boron and silicon mixed with phosphorus. Let's take phosphorus first. It has 5 electrons in its outer shell. When it links up with silicon, there are only 4 holes, so an electron is free to move about. This is the key. Free electrons can be corralled to follow a certain path. This flow of electrons is electrical current. A combined measure of the current and voltage of the cell tells you how much power the cell produces. This is measured in watts. But wait, our solar cell isn't quite finished. To corral the free electrons, we need a second layer to our cell, one that attracts those electrons. What's going to make them move in a certain direction? Another hole with a positive charge, that's what. Think about that magnet again. For this to work, we need negatively charged electrons to seek out positively charged holes to fill. This is where silicon mixed with boron plays its role. A boron atom has 3 electrons, and you guessed it, when it connects with the silicon, there's 1 hole left over. If we put 1 layer of the silicon phosphorus here and the silicon boron layer here, the free electrons can't help but be drawn to the positive side. But if all the free electrons filled all the holes in the positive side, this wouldn't be much of a device. The key here is where the electrons cross the barrier. This is called a junction. You have to imagine that tons of free electrons are trying to make it across and moving very quickly, and all this push and pull of positive and negative creates an energy field at the junction that works to attract electrons. It's like a line of people going into a theater to see the best movie of the summer, and everyone in line is doing jumping jacks, and all of that crazy activity attracts more people to line who start doing jumping jacks, and so on and so on. The energy that puts this whole thing in motion? Sunlight in the form of photons. Now we're ready to put it all together and make solar energy. We combine a number of solar cells into a panel, and now we have capacity. Combine a number of panels, and we have a system. The modular nature of solar energy systems allows us to design an array to meet electrical demand. Need more power? Add more panels. It's not quite that simple, but you get the idea. Solar panels are made up of a series of layers. Different types of panels use different types of layers, but all of the panels have common elements: collect sunlight, reduce reflectivity, channel the electrons, attach together, and attach to the roof. Silicon is super shiny and will reflect most of the sunlight that hits it. This is not optimum. In traditional glass panels, there's a sturdy base for support of the whole structure, then the silicon boron layer, and then the silicon phosphorus layer. On top of that is a contact grid composed of wires that collect the electrical current and direct it out of the panel for connection to other panels or pieces of the system. Finally, there's an anti-reflective coating and a glass cover for protection from the weather. Traditional panels can be linked together in an array designed to meet your power needs. For optimum sun exposure, those panels must be angled just right, most often toward the south, and require a mounting system for use on rooftops. Advances in technology and innovations in design have led to new panels called thin film or flexible solar panels. They're based on all the same principles of traditional glass panels, but ultra-thin materials and a flexible backing make for an ultra-thin solar panel that's rolled out in long strips and adhered directly to the roof surface. Thin film PV panels measure less than a quarter inch and weigh less than a pound per square foot. Like glass panels, thin film panels are composed of layers, but that's where the similarities end. FlexLight is a thin film solar laminate made by Unisolar. It has 6 layers that collect sunlight and convert it to electricity. Let's start at the bottom and work our way up. The bottom layer is a flexible stainless steel substrate that attaches easily to a variety of roofing materials, like metal and membranes used for flat roofs. Next, there is a layer of reflector film, and on top of that, 3 layers where the conversion of sunlight to electricity happens. The whole thing is covered in a final layer of transparent conductive oxide film. We have to take a quick sidebar here to discuss some important differences between crystalline and thin film panels. These layers are made of amorphous silicon, or ASI. Unlike crystalline silicon, or CSI, amorphous silicon features irregular atomic arrangements. In other words, they lack the regular patterns of crystalline structure. Amorphous silicon is created by melting and rapidly cooling CSI with a plasma vapor deposition process. I know, it sounds like science fiction, but this is what makes thin film solar cells possible. And manufacturing the flexible panels can be done on a large scale, quickly and efficiently. Using FlexLight as an example, the 3 layers are amorphous cells with different light absorption properties. This is accomplished by using different compounds of amorphous silicon. One layer is simply ASI, designed to capture low light. The next is ASIGE, or a silicon germanium layer designed to capture filtered light. The last of the 3 is also silicon germanium, but in a slightly different mixture that's great at capturing bright sunlight. All 3 together capture the full spectrum of light, which is quite different from the structured crystalline panels. Whether you're using crystalline or thin film PV panels, after mounting and running the requisite wires, the rest of the system is quite the same. Aside from any orientation needed for optimum exposure to direct sunlight, panels can be arranged in a series to provide a little or a lot of power. A certified installer will help you determine just how much power you use, and in turn, what combination of panels will provide the optimum wattage for your needs. The connecting wires on the rooftop are typically run in covered channels, streamlining the installation. These wires go to an inverter. In our case, the solar panels generate direct current or DC power. Household and office appliances use AC or alternating current. The inverter changes DC to AC to make the power usable. The inverter is connected to the building. The building has an internal electrical system that delivers power to every room and every outlet through a central distribution panel. The building is connected to the grid, the local electric system run by the regional utility or power company. Aside from sitting on the roof and watching the sunshine on the panels, it's difficult to monitor a solar energy system and see how well it's working. Some inverters have a display panel that tells you the current output and tallies up daily, weekly, monthly, or yearly production in kilowatt hours. Once again, innovation and technology make it possible for you to monitor FlexLight in an informative and interactive way. Advanced Green Technologies has an exclusive online monitoring system that not only tracks your energy output from your FlexLight system, but sends an alert anytime there's an indication your system isn't operating properly. The system monitors energy generated in watts and kilowatt hours and keeps totals each day, week, month, and even over the lifetime of the system. The monitoring system is easily accessed from any computer, and when displayed in the lobby or waiting area, it clearly demonstrates your commitment to environmental responsibility and solar energy. Solar energy is abundant and renewable. Solar energy systems are technologically advanced ways of harnessing that power. Embracing these technologies is an important way to be a good citizen of the planet. So let the sun shine in and see a bright future tomorrow and every tomorrow after that.